Welcome back, students. This is Thermodynamics Lesson 2. This is called calorimetry. So, we will use calorimetry data and we will determine enthalpy changes. We will explain in a general way how stored energy in chemical bonds originated from the sun. And we will talk about the state of water in various situations, photosynthesis, combustion. Calorimeter is simply a device filled with water used to trap heat. In simple demonstrations, we can use styrofoam cups and pop cans. Industrial applications, we use bomb calorimeters. So, there's some examples. There's what we might see in a typical high school classroom, and here's a more advanced form, which is very, very accurate. Okay, now let's jump back to this just for a second. Let's remember that the energy stored in chemical bonds originated from the sun. Okay, so photosynthesis, remember CO2, H2O go into the plant as well as sunlight, and that energy is represented by those. And then we make glucose and oxygen, and the glucose has energy, this energy stored in it. And then the plant cells take the glucose and burn it, and then they get that energy out of it. So the molecule glucose has energy stored in it, and it just came out there when this reaction happened. So in every cell, kilojoules are being used to do the processes inside the plant cells. Okay. We also need to know the laws of thermodynamics. The first law is matter cannot be created nor destroyed, only converted from one form to another. So we might have carbon dioxide, and it has a carbon in it, and we can break the carbon dioxide into C and O2, but we can't destroy the carbon itself. We can rearrange it, but we can't destroy it. And we can't create it either. It was given to us from somewhere. Second law of thermodynamics. Heat flows naturally from hotter objects to colder ones. So I always use the example, if you put an ice cube in your hand, heat isn't, or cold isn't going into your hand. Heat is leaving your hand, making it feel cold. Okay. Now, let's talk about calorimetry. We need to talk about the state of water. In combustion in an open system, we will produce CO2 gas and H2O gas. So there's our barbecue we used in the last unit. When we burn propane, and this is an open system, it's just out in the atmosphere, right? This propane will give off H2O gas, okay? If the same thing were placed in a calorimeter, if propane were burnt in a calorimeter, in our course, we will say that H2O liquid was given off, because this is a much colder environment. It's surrounded by water. Okay, that is a simplified view of it, but in our class, that's what our curriculum calls for. And in photosynthesis and cellular respiration, we'll be dealing with H2O liquid. So, of course, the water that goes into the plant is H2O liquid, and when this happens, we have H2O liquid in our cells or in the plant cells. We wouldn't want H2O gas. That would mean in our body, if we ate some glucose and H2O gas was given off, that would mean it would be over 100 degrees Celsius. That probably would not feel good inside your cells. Okay, moving on. Formula for calorimetry. Heat lost equals heat gained. So I'm going to symbolize it like this. Heat lost equals heat gained. Now we're going to use that formula for the rest of this lesson. Heat lost equals heat gained. Okay, let's take a look in more detail. So let's imagine in a research laboratory we burn 3.50 grams of ethanol in a sophisticated calorimeter. This causes the temperature of 3.63 liters of water to increase from 19.88 to 26.18. Use the evidence to determine the molar enthalpy of combustion of ethanol. Okay, that's a lot of words. Okay, we're burning 3.5 grams of ethanol. So we take our ethanol, and that goes inside the bomb of our bomb calorimeter. Okay. Now, 3.63 liters of water will increase from 19.88 to 26.18. So heat will be given off to our calorimeter. So now we know that our heat lost equals our heat gained. Our heat lost by ethanol, the ethanol is kicking heat out to the water and the surroundings. Heat lost by ethanol equals heat gained by the water. Now, we have to ask ourselves, is ethanol going through a temperature change or a chemical change, like we learned in lesson 1? Well, ethanol is burning, so we know it's a chemical change. Our formula for chemical changes is delta H equals N delta HM. And so the calculation part of that is moles times molar enthalpy. So that will be our formula for this side of the equation. Now, is the water undergoing a temperature change or a chemical change? Well, the water is going through a temperature change, and our formula is mc delta T. So we will put that up there like so. So now heat lost by ethanol equals heat gained by water. N delta HM for ethanol equals mc delta T for water. This energy equals this energy, right? The arrows that left are gained by the water. Now we got to find the molar enthalpy of combustion of ethanol. Okay, so I want to solve for delta HM. That's molar enthalpy, potential energy that was given off by the ethanol. So I need to isolate that. I get N by itself, or I get delta HM by itself by dividing by N. What I do to one side, I do to the other. And make sure that I write my substance down. That's moles of ethanol. N's cancel, and now I have my formula. So I will plug in my mass of water, which is right there. And you know that 3.63 liters when we're dealing with water is 3.63 kilograms. I'll times that by C, which is 4.19 joules per gram degrees Celsius. Now, because I have kilograms and grams, I want these to cancel nicely. Here's what I can do. I can change this 4.19 to kilojoules and this one to kilograms. So here, 4.19 little joules over a little gram versus 4.19 big kilojoules over a kilogram. So you can do that. And students think that that's like breaking some law, but it's not. If you think about it, you can just see that you're just dealing with larger amounts, and the larger amount on the top corresponds to the larger amount on the bottom. And now I do my temperature change of 6.30 degrees Celsius. I will divide that by N, and I know N is of ethanol, so I take my mass times by my molar mass. You can see what I'm doing there, canceling my units. Okay, and now I cancel kilograms, I cancel degrees, I cancel grams, and I'm left with 1260 kilojoules per mole. I know it's exothermic because these arrows were coming out of ethanol. Ethanol was releasing heat, the water got hotter. The water is endothermic, it absorbed heat, but the ethanol is exothermic. And I can then change to the correct significant digits, which will be 3, negative 1.26 megajoules per mole. Okay, perfect. Now here's another example. We have 2.65 grams of sodium hydroxide added to 20 milliliters of hydrochloric acid. The temperature rises from 25 to 29.4. What's the molar enthalpy of neutralization? Okay, so I take some sodium hydroxide. So there's my sodium hydroxide, and I got hydrochloric acid here. Okay, 2.65, that's a poor graphic. 2.65 grams of sodium hydroxide is added to 20 milliliters of hydrochloric acid. We stir it all up, it dissolves, and the acid neutralizes the base. Anyway, they react. Heat is given off because we know the water went from 25 to 29.4. Okay. Now, what is the molar enthalpy of neutralization? Okay. The question does not say the word calorimeter, but water is clearly rising in temperature, meaning it's gaining heat from somewhere. If water is gaining heat, something's losing heat. In other words, this is behaving like a calorimeter in that heat lost equals heat gained. So heat lost equals heat gained. Now this gets a little tricky. We're going to go heat lost by the sodium hydroxide equals heat gained by hydrochloric acid. But I know that hydrochloric acid is mostly water. And it'll just make it easier to think about how this works. So we're going to say H2O liquid is what's gaining heat. Okay, the water is going through a temperature change, MC delta T. Now, is this going through a temperature change or a chemical change? Well, neutralization is a chemical change. What's really happening is NaOH is reacting with HCl, and it's a chemical reaction. We made new chemicals here. So that's a chemical change. So now we have N delta HM for sodium hydroxide equals heat gained by water. Okay, we divide by N, and make sure we know the substance. It's moles of sodium hydroxide, not water, because the N came from over here. And I plug in my mass, 20 grams, 20 milliliters is 20 grams, times by 4.19 joules per gram degree Celsius, times by the temperature change, divided by my moles of sodium hydroxide. My molar mass is 40.00 grams per mole. I invert that, cancel my grams. There's the cancellations, and we get 5565 joules per mole. And I can change that to 5.57 kilojoules per mole because I need 3 significant digits. 3, 3, 3, 4, and we don't count temperature, we just ignore that. So, it's for sodium hydroxide. Sodium hydroxide gave the heat away when it reacted with hydrochloric acid. The water went up because sodium hydroxide gave away heat. Therefore, because the question's asking about NaOH, the NaOH is negative. It gave away heat. It's exothermic. There's my final answer.